These will be the two last lectures of QBronze before everyone can finish the module this week.
Hello, everyone. Great to be back. I need to catch up on the conversation on Discord. I just quickly reviewed the statistics and the quizzes on Canvas, and it seems like we are kind of evenly matched. There are about at least 260 plus students have attempted a quiz from Bronze. And right now I see there are about 230 odd people in our workshop. People might be watching this offline as well, right? So just a reminder to everyone to complete the requirement for this part of the workshop. There are 5 quizzes on Canvas that you can attempt until July 25th. I think there are about 30 people who have already gone through the entire 5 quizzes, so that's great. Hopefully that 30 will also become 300 by the time we reach the completing requirement. All right, everyone, welcome back to our 4th session for QBronze. And today, hopefully, we finally get to the fun stuff in some sense, interesting protocols from quantum computing and quantum information processing as well. Quick summary of what we've been talking about over the last 3 sessions during the workshop regarding quantum systems. We saw the state representation for quantum states and qubits, which can be viewed as essentially just the state psi, which is in an arbitrary superposition of all the basis states, where you imagine this I to be, let's say, the binary representation of n bits. So take n bit string, so you can start from 000 all the way up to 111, and this I essentially represents that basis state. And you can have an arbitrary component. Recall, for the purpose of our QBronze workshop, these amplitudes are restricted to real numbers. And so the requirement for the interpretation of these amplitudes as probabilities means that the sum of all these alpha I squares has to equal 1. We also saw that evolution over time would be captured by this unitary matrix. So we apply unitary matrix to a state psi to obtain a state phi. The requirement that phi is also going to be a quantum state essentially means that this U has to be unitary. We'll have more to talk about that, discussed today. And finally, also that measurements mean that when we look at this quantum state, the probability with which I will get state I as my measurement result will be alpha I squared. Right? So those 3 were the kind of the 3 main takeaway points regarding the quantum formalism that we've discussed. And what we finished off last time around was this poster child example of quantum information, i.e. a Bell state. So this simple circuit where we start off with 2 basis states 0, 0, perform Hadamard on the first qubit, and then followed up by a C0, results in us obtaining entangled quantum state, also referred to one of the Bell states. And we'll have occasion today to see multiple examples of this Bell state being used as a resource for the purpose of performing information processing tasks that are generally not possible using only classical information. Any queries, concerns, questions, issues, remarks that people would like to bring up before we continue? So we'll have 2 circuits to discuss today to begin with. The first protocol is called Superdense coding. Quickly review what this circuit is representing. So this dotted line represents physical separation between 2 parties that we're interested in, let's say Alice and Bob. This physical separation may be arbitrarily large. And the idea is that between Alice and Bob, there's a resource, a quantum resource shared in this form of the Bell state phi plus that we just mentioned. I'll write it down over here as well. So Alice and Bob share the quantum state. So when you look at this mathematical representation, the way you can kind of imagine is that this first qubit over here represents the qubit that in this case, let's say, is with Alice, whereas the label in each of the ket represents the qubit that's with Bob. Is the C0 of the Bell state in 4D? The matrix representation for the C0 gate would be a 4x4 matrix, right? So yes, it would be a 4x4 matrix, unless I'm misunderstanding your question. Back to the circuit. In the circuit, as we've discussed in the visual representations that we did with Qiskit, 2 parallel lines like this represent evolution of our transmission of classical information. So you are starting out with 2 classical bits A and B that are known to Alice. Moving from left to right is kind of our evolution over time. These 2 gates are being applied by Alice, conditioned on the first qubit, which the first classical bit A. She will apply Z operator. So the Z operator, which we discussed last time as well, has this representation. But this is a control Z operator, right? So it's a 2-qubit operator. The idea is conditioned on the value of the first qubit. If the value of bit A is 1, then apply Z gate to Alice's part of the qubit. And within our representation, that would mean that the Z gate gets applied on the first qubit over here. The second qubit, remember, is with Bob. Then we have a second gate being applied by Alice again, a conditional operator where condition on the value of B, if B is 1, apply a NOT gate on Alice's part of the qubit. We know this as our standard C NOT gate. Then this qubit is transmitted by Alice physically to Bob, right? So there's actual physical transmission of this qubit from Alice to Bob. Bob now gets this qubit, and Bob has kind of this operation to, or the sequence of gates to apply. It seems very familiar. It's kind of just a reverse operation of what we did for the preparation of the Bell state. We'll see what that results in, as noted over here. What this means is that if Bob will perform now measurement on his part, he's supposed to get A and B exactly as his measurement result on his end. And obviously, we already see the consequence that the 2 bits that were with Alice have now effectively been communicated to Bob at the expense of 2 kind of resources, right? So at the expense of Alice and Bob having access to prior shared entanglement, at some point they received their share of the state 5+, and Alice being able to actually physically transmit or communicate her qubit to Bob. So there's a quantum channel that's needed for the ability of Alice to transmit this qubit to Bob. We'll work through the computation of this circuit in the next slide, but I just wanted to make sure everyone got kind of the bigger picture here. Any questions about the visual description of the circuit? Sure, yeah, you're right. So this isn't exactly the creation of the Bell state. It's the reverse of that operation, exactly. And we'll say more about this soon. So this is not the teleportation circuit, that at the end you're getting 2 classical bits are being obtained by Bob at the expense of communication of 1 quantum bit, although the 2 circuits are very similar. I can discuss quantum channels in more detail, essentially the idea being having the ability to transmit a quantum state, but we won't have occasion to essentially talk more about within our discussion right now. How to share the 5+ state. So you can just assume at some point, the simplest example would be Alice and Bob actually physically met up at some point where they themselves prepared the state, or someone else could have provided them their individual share of the 2 qubits after preparing it. Superdense coding is not equal to teleportation. It is very closely related in some sense, which we'll talk about once we've seen both these protocols. A good question. Does there exist a way to send more than 2 classical qubits? No. So at the expense of transmitting 1 qubit, there's something known as Holloway's bound. This is a tight bound. So we can't transmit more than 2 classical bits using 1 qubit. Right, so in this case, we haven't transmitted 2 qubits. We have transmitted 1 quantum bit, and Bob has gained the ability to receive 2 classical bits of information. So let's try to work through the computation. Maybe some of the questions will be answered by the computation process. So we have partitioned logically the circuit into time steps T0, T1, T2, T3, T4. And what we'll just do is kind of a brute force verification, where we'll start out with the 4 possibilities of the values of the 2 classical bits A and B, and see what is the state that Bob is left with at time step T4. Right, does that make sense? The name of the bound I just mentioned was, so how about people shout out the answer on Discord or in the chat? We are trying to fill in the first row over here with the idea that Alice and Bob share the state 5+, and the value of AB, the 2 classical bits AB, is 0, 0. So what would be the state, quantum state, that Alice and Bob share? I.e., I'm not going to keep repeating the values of A and B. Rather, all that I'll write down is how the state 5+ is evolving. And so I'm interested in first figuring out what the state will be at time step T1, condition that A and B had value 0, 0. So nothing fancy happening over here so far. So at state time T1, the state shared between Alice and Bob will continue to be the state. This quantum, I'm interested in the evolution of this quantum state 5+. Alice and the joint state. So I want to write down a description of the joint state shared by Alice and Bob at time step T1, given that Alice has now applied this condition Z operator. So conditioned on the value of A, apply a Z operator on her share of the qubit. Recall that this is a conditional operator. Because A is set to 0, nothing will change. So the state remains to be 5+. State time step T2, same idea. It's a control operator. The control value is 0. And so nothing will get applied on Alice's share of the qubit. And so we continue to have 5+. At time step T3, what has happened is the qubit, Alice's share of the qubit, is now received by Bob, and Bob now applies a control NOT. Control qubit is the first qubit, and the target qubit is the second qubit. How will 5+ evolve? By evolution, by application of the C NOT operator on it. So we have got 0, 0 plus 1, 1, and we're applying the C NOT on it. So naturally, 0, 0 doesn't change. 1, 1 will change. The first qubit is controlled, so 1, 1 will evolve to 1, 0. And so we get the state 1/2 √2, 0, 0 plus 1, 0, right? Note now the two qubits have actually become unentangled. I can write down this state as 1 over square root 2, 0 plus 1 as the first qubit, tensor 0 for the second qubit. And now based on this, it's obvious what T4 state will be, given that now we are applying at time step T sub 4, we have applied Hadamard on the first qubit. The first qubit is in the plus plus state. And so the state at this T sub 4 will be 0, 0. Great, that's what we were expecting, that the two qubits are in the state AB. AB was 0, 0. So the state that we have is 0, 0 as well. Time step T sub 1, given that Alice and Bob, or Alice has AB set to 0, 1 respectively. A is still 0, so control Z will not get applied. So the state 5 plus remains unchanged at time step T sub 1. We've got 5 plus again. However, B is set to 1 now, so the C naught does get applied. But note now what will change in the state 5 plus. It's the first qubit that will get flipped, conditioned on the fact that the B bit is set to 1. So what will be the state at time step T sub 2 now? 1, 0 plus 0, 1. Excellent. Right, so what has happened? Note, all that we've done is essentially just flip the first qubit in both these. The first qubit gets communicated to Alice, to Bob. Bob applies now a C naught condition on the first qubit again. This state now evolves to 1, 1 plus 0, 1. Excellent. 1, 1 plus 0, 1, which again can be simplified to 1 square root 2, 0 plus 1, tensor 1. And that then gives us 0, 1, exactly what we would have hoped for. 1, 0. Now the control Z gate does get applied on the first qubit that Alice has, conditioned on the value of A being set to 1. So rather than 5 plus, now the starting state is for 1, 0. At time step T sub 1, the state is only the sign in front of 1, 1 will get flipped because the Z operator flips the sign in front of the 1 state. So we get the state 1 square root 2, 0, 0 minus 1, 1, also referred to as phi minus. This state now moves forward at time step T sub 2. Does anything change? No, because B is now set to 1. So this remains 1 over square root 2, 0, 0 minus 1, 1, the phi minus state. Time step T sub 3, 0, 0 minus 1, 0, because of the application of C naught, which we can rewrite as minus 0, right? Because the sign in front of 1 is minus. Apply Hadamard to the minus state, you get 1, 0 out. Our answer is what we would expect. Quickly finishing this off for the case 1, 1, 0, 0, minus 1, 1. Evolved. Now the C naught also gets applied. And so the state is 1 over square root 2, 1, 0 minus 0, 1. C naught now again gets applied with the first qubit as control. So 1, 0 becomes 1, 1, which is equal to minus 1. Oops, sorry about the bracket. And so that gives us just exactly what we expect, with addition with a minus sign, which doesn't really matter, because when we measure this state, we will still get 1, 1 with probability 1. So that's a quick verification of the superdense coding protocol. What have we achieved here? Perhaps it doesn't seem that great, but still, something that's not possible classically in general, that via the transmission of 1 qubit, Alice has been able to communicate to Bob 2 classical bits. So that's kind of a general protocol that you can assume Alice and Bob could always do, where a classical information that requires communication of n bits can be moved to a quantum protocol where the communication requirement would now become n over 2 classical bits, with the expense of adding this physical requirement of having the ability to communicate quantum information rather than classical information. So naturally, it's not going to be as easy as, well, at least with current technology, that Alice just picks up a phone and communicates the quantum state, right? Because while we can communicate classical information that way, at the moment, we can't really communicate quantum information that way, right? You can do this using matrix method as well. You can just do standard matrix vector multiplication as well and do it that way. That's perfectly fine. The more you kind of do these calculations using Dirac notation as well, hopefully the more you'll become familiar with it as well. Alice has 2 classical bits and 1 quantum bit, so not 3 qubits. You can imagine those 2 classical bits as qubits as well, but the idea is that these 2 classical bits, these 2 values cannot be in superposition. They are actually classical values, classical bits, and only Alice has 1 quantum bit, Bob has 1 quantum bit, both of them entangled in form of the Bell state. And at the expense of communication of 1 quantum bit, or communicating 1 quantum bit, Alice has been able to transmit 2 classical bits, also at the expense of actually what you would say using up the entanglement as a resource, right? So 5 plus, the 2 quantum states were entangled at the beginning, whereas by the end, that state is kind of complete, that entanglement is completely gone, right? So the state that Alice and Bob are left with at the end of this protocol, Bob has both the qubits, and they're exactly in this kind of product basis states, either 00 or 01 or 1011. So entanglement has been used up as a resource in the process of this protocol that allowed Alice and Bob to complete this task. All right. And what we'll want to do now is contrast this with teleportation when we move on. So just remember the key details of the protocol. Yeah, so it's not something that you would shout out regarding, hey, here's the key killer app for quantum advantage kind of protocols, but it's definitely something, at least, and this is what it was treated as well historically, is that here's kind of a key, an example of an information processing task that is not possible to achieve classically, but can be achieved quantum mechanically. You can do it for sure using classical communication, but then there's kind of this, what's being referred to in the title, this compression that's happening. You won't achieve that generally using classical communication. Right? So if you view classical bits as kind of a lesser resource than quantum bits, then you would agree that 2 classical bits have been communicated using 1 quantum bit, because computer scientists and physicists couldn't come up with a better catchy title other than Superdense. Teleportation, on the other hand, so if you think Superdense coding is kind of like a boring title for the protocol, teleportation then kind of is a misnomer, as we discussed. In some sense, yet, so you can view the 2 circuits for teleportation and Superdense coding as the opposites of each other. We'll touch on this and review this when we've seen both of them. So I think let's move on to teleportation circuit. So similar to Superdense coding, here's the protocol, here's the circuit for quantum teleportation. Whether or not we should actually call it teleportation, we'll kind of discuss after reviewing the protocol. You can kind of see what's happening is that there's the state psi with Alice, and there's this another quantum state with Alice, which is part of her share of the entangled Bell state 5+ with Bob. So to begin with, there is no classical information in the protocol. Alice has 2 qubits, and Bob has a single qubit. Bob's qubit is entangled with one of Alice's qubit to form the Bell state 5+. And in addition, Alice has another qubit psi. Note, as we'll touch upon later as well, we are not actually giving a description of what the state psi is, as Kush is asking as well. The state description of Alice may indeed actually be unknown to Alice as well. Alice need not know what the state psi is. Imagine someone just hands over Alice a black box for transmission and say, hey, here's a top secret quantum bit that I want you to transmit to Bob. And Alice will be able to perform this task without knowing what psi is. So that's kind of one of the key nice features of this protocol. Alice performs this certain processing task, which we'll calculate through, and then performs measurement on the 2 qubits that she has. This will result in 2 classical bits obtained by Alice. Those 2 classical bits, interesting, 2 classical bits are the result of the measurements now, whereas those 2 classical bits were the final result in Superdense coding. These 2 classical bits are then the bits that are communicated from Alice to Bob. Bob, on receiving these 2 classical bits, performs a certain bunch of protocols, certain gates. We'll see the significance of them soon. They're exactly the similar gates that Alice had applied on her end in Superdense coding, a C0 and Control Z gate. And we are claiming that at the end, Bob will be left with exactly the state psi that Alice started out with, even though Alice did not know what psi was, the description of psi. How is the measurement connected classically? I'm not sure I understand. Question. The idea is there were 2 qubits that Alice has. Alice performs a measurement in both of them. The result of that measurement, we call, is a classical label, right? We had described a qubit as having 2 states, 0 or 1. So one of those 2 will be the result of the measurement result. Those 2 classical values, labels, are then communicated to Bob. Okay. Questions about the teleportation protocol, the visualization of it at least? Teleportation as copying a qubit? If yes, is this against no? No. So there is something in quantum information and quantum computing known as no cloning, i.e. in general, you can't have a copy machine for arbitrary quantum information. And as you note over here, just in the visualization, this state psi that you can imagine starts out in an arbitrary value of a qubit alpha 0 plus beta 1. Is not in this state after the measurement result. After the measurement result, the value over here will be with a certain probability, either 0 or a 1. When we claim that Bob now on his end has received psi, this is in no way violating or allowing Bob to copy Alice's state psi, because Alice now no longer has a copy of psi. So this is not at all performing copying, rather it's some form of transmission of the information from Alice's end to Bob's end. We cannot understand express qubits without classical references. I'm not exactly sure what you mean by the question, but yeah, underlying the idea is that, and this is an interesting feature for some current quantum algorithms as well, and future quantum algorithms. Much of the initial research in quantum algorithms, for example, was also just assuming that for sure the result of any algorithm is going to be, some classical information as a result of measurement. But when you're talking about genuinely quantum processes, then you could imagine two quantum processes such that one process gives as output a quantum state that then is fed as input to another process. So in that case, there is no measurement performed, but the two processes are still interesting quantum algorithms. And the idea is that one quantum algorithm results in a quantum state that is then fed as input to another quantum algorithm. But if you're thinking about any process where a measurement is occurring, then yes, the idea is that the result of a measurement is always going to, for us, be a classical label. What exactly has this protocol achieved? We'll talk about it a bit more detail after working through the computation for this protocol. So psi was the state arbitrary qubit that we label as alpha 0 plus beta 1. Tensor, the state phi plus that Alice and Bob share. Right. So this is 3 qubits now. The first 2 qubits, let's expand the state description out. We've got alpha 0 plus beta 1, tensor the Bell state. Expand this out, we get the state. So this is equal to 1 over square root 2 alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. Right. You can think about the protocols as performing a Bell measurement as well, but because we haven't talked about Bell measurements, it is possible to state the protocols perform a measurement in just the standard basis after having applied these kind of correcting or change of basis gates. But you're correct, Victor. You can imagine just performing a Bell basis measurement as well, and that works. Okay, we know that we want to perform a C0 and a Hadamard, so let's perform a C0 first on this. So it will look something like C0 tensor identity, which results in the updated state looking like what? So it's an interesting computation push that you can do with that. What happens in this protocol if Alice and Bob, rather than sharing the state phi plus, were sharing some other quantum state? Maybe it's entangled, maybe it's not entangled. And what as one might imagine comes out is that the degree of success of correctly performing this teleportation of the quantum state depends on how close you were to a Bell state. The more entanglement you have, the higher the probability of correctly performing the protocol. But I leave this as an exercise. Right, so we perform the C0. Obviously, alpha 0, 0, 0 remains unchanged. Alpha 0, 1, 1 also remains unchanged, right? Plus beta 1, 0, 0 will now get updated to 1, 1, 0. I shouldn't really put me the bracket over there. 1, 1, 0 plus beta 1, 0, 1. All right. Now, little bit messy computation. We apply the Hadamard. So the first qubit expands out. Let's write it out. So after application of Hadamard on the first qubit, what do we get? We get a factor of half now out as general, and you get alpha 0, 0, 0. But that 0 will expand out into a factor of 1 as well. So you also get alpha 1, 0, 0, 0, right? And alpha 0, 1, 1 plus alpha 1, 1, 1 plus beta 0, 1, 0 minus beta 1, 1, 0, right? And finally, plus beta 0, 1, 1 minus beta 1, 1, 1. Everyone okay with this expansion? Not 1, 1, 1, 1, 0, 1. Sorry, I messed up the last two states. This was beta 0, 0, 1 minus beta 1, 0, 1. Everyone agrees with this expansion? Now, because we are going to form a measurement on the first 2 qubits, and then conditioned on the value of these measurements, we are going to apply some control operators on the third qubit. Let's kind of just logically rewrite this 3-qubit state by pairing up or by collecting together the value of the first 2 qubits, right? So it's kind of like, what if the first 2 qubits are 0, 0? What's the value of the third qubit? What if the first 2 qubits are 0, 1? What's the third qubit? And so on and so forth. So towards that end, so what if we say you've got half 0, 0? In this case, what's the value of the third qubit? Well, we just go through the 2 cases in which we've got 0, 0 as the value for the first 2 qubits. We've got 0, 0, 0 and 0, 0, 1 over here. So it won't exactly be 5 plus, if that's what you mean as the value of the third qubit, right? So it will be alpha 0 plus beta 1, kind of exactly what psi is, if not. So you've got alpha 0 plus beta 1. So that's good. Now, what about the case when it's 0, 1? Well, there's this possibility of 0, 1, and then there is this possibility of 0, 1, right? And we already note that what is different here now is that the amplitudes are flipped. You've got an alpha in front of 1 and a beta in front of 0. for the moment, let's just write it out. So in the first two qubits are 0, 1. Then the third qubit is in the state alpha 1 plus beta 0. Right? You get the drift. If the first two qubits are 1, 0, then the third qubit is in alpha 0 minus beta 1. And finally, when they are 1, 1, then the fourth qubit is, third qubit, sorry, is alpha 1 minus beta 0. And so you can kind of already imagine what these two operators then are doing over here. These two operators are essentially kind of doing error correction for us in the protocol. That in the case when the two measurement results were 0, 0, Bob actually is already getting exactly the state that Alice had. That was the goal of our protocol in some sense as well. So nothing needs to change. So these two gates don't do anything. In the case when the measurement result is a 0, 1, i.e., we will need to apply a C0 gate in order to flip these amplitudes to get them right. If it's 1, 0, then we'll need to apply a control Z in order to get the local phase right, flip the minus sign. And in the fourth case, when both of them are 1, 1, we'll first do a bit flip and then a phase flip with control Z in order to remove both of those kind of errors. And that would then guarantee that in all of these four cases where the measurement results were 0, 0, or 0, 1, or 1, 0, or 1, 1, in all of the four cases, we will get exactly the state psi out. Let's quickly kind of write it out just to make sure everyone has it. Half 0, 0, alpha 0 plus beta 1, plus half 0, 1, plus half 1, 0, plus half 1, 1. And in this case, you've got an alpha 1 plus beta 0. In this case, we got an alpha 0 minus beta 1. And in this case, we got both of them happening, so alpha 1 minus beta 0. And so what you could quickly just verify, alpha 1 plus beta 0, when it goes through an X gate, which would be the control Z, control X, C0 working on this, you'll get exactly your alpha 0 plus beta 1 out, as you'd expect. When we have alpha 0 minus beta 1, alpha 1 minus beta 0, alpha 1 plus beta 0, you apply the, I am confusing the two states. In the second case, we have got alpha 0 minus beta 1. In that case, you apply the Z gate and you get back out alpha 0 plus beta 1. Well, in the fourth case, where we had alpha 1 minus beta 0, you apply the sequence. So first you apply the X gate, that gives you alpha 0 minus beta 1. Then you apply the Z gate, and that gives you back alpha 0 plus beta 1. Computation is done. Now to sit back and kind of see what has happened. The circuit for superdense coding and teleportation. As we already kind of made a reference to, note that here you've got your control Z and C0. Here you've got your C0 and control Z. Here you had your C0 and Hadamard. Here you have your C0 and Hadamard. One quantum bit transmitted to get two classical bits. Two classical bits transmitted to get one quantum bit. Previous page, there you go quickly. Teleportation is more expensive since it uses two classical bits to transmit one qubit. Let's talk about it a bit more, right? So it depends how you quantify which one is more expensive. There's interesting nuanced things to note actually first about the quantum teleportation protocol that may not be obvious right away. So first of all, compare it to Star Trek teleportation. Is this beam me up Scotty teleportation that's happening over here? And so there was this state over here that Bob has attained over here. This is not. So why is this not Star Trek teleportation? Why do we call it teleportation then though? In what way is it similar to teleportation? There's kind of an interesting historical anecdote regarding the paper. There were 6 authors, all of them pioneers in quantum information, who authored the initial paper on quantum teleportation. And the story goes that the initial submission for this paper was not accepted. It didn't pass the review process. And then it found its way to David Mermin, who basically gave his decision to have it published right away. It's available online, the entire story. And there's an interesting thing that's happening over here that I think pervades many of theory of quantum computing. That the math over here is relatively easy to follow, right? It's essentially just high school or matrix algebra calculation. The math over here is not at all fancy. That was kind of one of the claims of the initial review of the teleportation paper as well. But it's really the interpretation of what has been achieved, right? One thing to emphasize is not, as everyone is saying, hey, it's not teleportation. One of the reasons is in Beam Me Up Scotty, they would go to an unknown planet for the first time, have never been to that planet. There's no lab set up on the surface of that planet, and yet you're able to teleport yourself to the surface of that planet, right? That's not what's happening over here. Alice and Bob need to have met up prior. They need to have shared entanglement among themselves, and there needs to be some post-processing happening on the lab, on Bob's end as well, in order for Bob to finally receive what he has, the state that Alice wants for Bob to receive. At the same time, also, this is not faster than light communication as well, because before these two classical bits are communicated to Bob, Bob has no way of knowing what state he has over here. Or for sure, his state is definitely not going to be always the state psi. He needs to be able to perform this error processing in order to ensure that he always has the state psi. Although it's obvious, but I guess it should be emphasized in order to make sure you don't get dissuaded by some popular science articles. There's no faster than light communication happening over here. Psi is not instantly teleported to Bob, because Bob must wait for these two classical bit results. Alice needs to call him up, tell him 00011011 in order for him to be able to perform these tasks, and only then does he always have the state psi. Yet at the same point, there are something more interesting nuanced things that are more interesting than what's happening in superdense coding. We emphasize the fact that psi was an unknown state even to Alice, right? So you could imagine that this state psi has been, created with really high precision, and these alphas and betas somehow are encoding the entire works of Shakespeare or entire English literature or some other, big piece of knowledge. And the binary encoding of alpha and beta encodes exactly that. It's not as if the amount of communication that needs to be transmitted by from Alice to Bob depends on the precision level of, how precisely do we need to know alpha and beta. These two classical bits guarantee, in a noise-free situation, that exactly that same alpha and beta have been teleported to Bob without any additional resources. Just these two pieces of classical information. So that's interesting. Having said that, though, it's not as if Bob can obtain that entire information via measuring the state psi. He has only a single state of psi, and that single state of psi is not enough to reconstruct a high precision alpha or beta. But yet, if the state psi needed to be used in computation with some other states, then that can still work out, because that exact alpha and beta have indeed been teleported to Bob. In addition, a good exercise for you is to verify that this protocol actually is even more interesting, because here we assume that this state was just this one lonely state psi. What is also possible for this teleportation protocol is that if the state psi was itself entangled with something else that David or Charlie had, then the resulting state psi that Bob receives over here at the end is also still going to be entangled with whatever Charlie or David had. So this teleportation preserves entanglement. So that's also very nice and cool. And so there are features of this teleportation protocol that are even kind of more interesting than standard teleportation, in the sense of this, entanglement being preserved, stuff like that. Yet at the same time, the structure of quantum information does apply certain restrictions on this protocol. It's not faster than light communication. It's not allowing you to get arbitrary high information just via the teleportation of transmission of two classical bits. There are restrictions, but yet there are interesting nuances to this protocol. And actually, one of the kind of initial discussion points also about this protocol was, well, this holds and works out when you're talking about just teleporting an individual qubit, much like the discussion around large-scale quantum computation. Would this teleportation protocol also kind of scale? It makes sense to think about, I've teleported the state psi, but if I agree that, or if I believe that quantum physics is a complete description in some sense of reality, does that mean if I take a complete physical description of my pet cat or myself and make it go through this process, I would teleport myself as well? I don't know. And the jury is out on how to understand that question, right? Miguel says yes, exclaims yes, perhaps not. I don't know. Depends on how you understand whether the total is greater than sum of the parts or not. But you note again that also the complexity of this algorithm, this protocol, would really increase as well as you increase the number of states that you want to teleport. For one qubit, we needed Alice and Bob to share one EPR state, and that keeps increasing as you keep increasing the number of qubits you'd want to teleport. Guess that's all that I wanted to emphasize here in terms of the points for this protocol. Any other questions about this protocol before we move on? How do you teleport two states that are entangled? So you could perform the teleportation protocol twice for each of the two states, right? Unlike superdense coding, we can teleport more qubits than, no, so you'll need to repeat the protocol, right? And so for each iteration of the protocol, you'll need its version of the EPR state. So note again here that over here, again, the Bell state that Alice and Bob were sharing is destroyed. So again, entanglement is consumed. Prior entanglement that both of them were sharing is consumed as a result of performing the information processing task that you were interested in. So for sure, this is a protocol that is really easy to state, but has lots of subtle features and nuances that it helps to keep going back to. And that's a feature of many kind of quantum computing tasks in general as well, right? That the math itself might be easy to work out, but the features itself or the interpretation of what has actually happened does take some time to kind of settle in. Actually, real life application, I think cryptography, other than cryptography, they're just like you're teleporting a quantum state over here. There's also, this has been generalized to teleporting quantum gates as well. And it's kind of one of the building blocks of many features, right? So when you want, let's say, transmission of a quantum state that can, over arbitrary large distances, and that can be set up by multiple iterations of the teleportation protocol as well. So there are lots of kind of practical implementation applications as well. So its limit on superdense coding comes from the Hulevo bound, which is a much more general result, but applies to superdense coding as well. This was the name. And so we won't definitely have time to talk about it, but you can look it up in any standard information theory text. How is this done in real life? That I'll leave for the physicists to talk about in discussions. It doesn't seem that bad, right? So you've essentially just got a control NOT gate, a beam splitter, a bunch of control gates again on 2 classical bits. So the issue here is more in terms of, can Alice and Bob preserve this shared entanglement for, if one was going to Mars and the other was going to Venus? Can we make a generalized equation for this protocol to transfer more qubits? So what you could definitely do is just iterate the protocol multiple times to transmit more qubits, right? As I mentioned, you'll need to consume a resource every time you're teleporting a qubit. So one EPR state consumed gives you teleportation of 1 qubit. Now you want to send more qubits or teleport more qubits, you consume more EPR pairs. So teleportation has been done in the lab. This is for sure doable. Like, I say teleportation, quantum teleportation, right? So this version of it is done. It's not the Star Trek teleportation. This could be done simultaneously. By this, you mean? So you do have entanglement in the lab, right? So that's fine. It's just that matter of preserving that entanglement longer time periods. While people are kind of reminiscing and discussing this, let's take a quick, not break, but review of something related to teleportation in popular science or in popular media.
At Underwood Sampson, we do not get paid for hunches. The reason why our fees are higher than any other firm is because of our unparalleled ability to not only assess value, but to create it in our clients' businesses. We do that by focusing on the fundamentals. This is a hypothetical business. Thanks to groundbreaking research, BMUS Transportation, using 11-foot-tall cylinders, can teleport travelers to any destination in the world instantly. Buenos Aires to Cairo in 1.5 seconds. I want you to tell me what the company is worth. Information is in your binders. You have 1 hour.
Okay.
Is he serious?
So that's as per the third quarter.
Please continue.
Because of these factors, I project the total value of BNUS at $48 billion, with revenue growing at an average 52% per annum for the first 2 years.
I'm not with you on the growth rate. Changas, I've got a 5-star safety rating from AB Towns. My travel cylinders only cost $11 million a piece. What is your analysis?
Your company is worthless?
What? Care to clarify?
Well, AB Towns is all well and good, but if your business is convincing a mother that you can successfully disarticulate and then reassemble all the molecules in her 5-year-old thousands of miles away, this technology is at least a generation away from practical widespread usage.
Is that a hunch because you're not getting paid for hunches?
No. Page 68, your own market surveys show 72% of your potential travelers would never use the cylinders no matter how safe you proved that they were.
So I should just pack up and go home?
No, I'm saying you should pack other people up and go into shipping. The same polling suggests that 94% of clients would be okay with you teleporting their baggage. So your business isn't travel, it's shipping, sub-container scale shipping.
All right. So that was it. So now you've got ideas about using quantum teleportation for business as well. We'll go back to our slides. All right, so let's finish off this discussion on teleportation and superdense coding. We'll finish off today's discussion, then setting up for what we'll see tomorrow in terms of Grover's algorithm. So we take now a shift to talking about computational problems and solving them using quantum algorithms. Towards that end, we focus on something that we identified at the beginning about quantum gates. We noted that quantum gates have to be unitary. We can connect that to the fact that, well, not all classical gates are unitary, i.e. reversible. I'm going to take a standard example like the AND gate. When you perform an AND gate, it takes 2 bits as input. 1 bit comes out as the output, but we've lost information about what the inputs were. So if I got the output 1 over here, then yes, I know the inputs were 1, 1. But if I got the output 0 over here, I cannot reconstruct what the value of xy was. Even if I just add another bit over here as output on the AND gate, I would still not have the value of both x and y, right? Because I still need the value of the actual AND gate as well. So you can, as an answer you might come up with just after thinking about this a little bit, the way you make it reversible, and even classically how you can make gates reversible, is in this case, you add 1 additional bit of memory, auxiliary bit, and this bit is where you end up then storing the result of your computation, right? So this would be one way to perform the AND gate in a reversible way classically. So you preserve what the inputs were, and you have an additional bit where you are storing the result of the computation that the gate needed to do. Naturally, now when we do these computations over quantum gates, these inputs need not be just classical input bits. They could be qubits, which could be in superposition and entangled as well. That's what we'll work out today, and one of the tricks using that. So the way you can think about applying any arbitrary Boolean function on quantum information is by basically saying, hey, all right, these are the bunch of bits, let's say. Imagine this A is the binary encoding of some n bits, and I wanted to apply some function f on these n bits. Let's say they have the value A, then that can be represented by this unitary B sub f. The way this unitary B sub f will work is by parodying in the output of the function f evaluated on A into this additional bit that we started out initiated with the value B. What does B sub f do? B sub f takes as input qubits in the state A and B and transform them into the form A and B being transformed into B parity f of A. Note that this is reversible because we can again just always apply B sub f again, and you'll again, let's say in this description, have a parity of f of A again. So if you apply B sub f twice, what you'll get is B parity f of A parity f of A. These two will cancel out to become 0, and so you get left with B. So you can reconstruct the original value of B. This ends up being good question. How we design the B sub f? Well, that really will depend on the description of f itself. And that's a whole big kind of discussion point as well in terms of designing these B sub f. We'll probably not get a chance to talk about this in bronze, maybe a little bit in silver. But obviously, the key thing will be you need to have the description of f. And once you have the description of f, you can use it to construct B sub f. In some cases, you might also say that, all right, B sub f is given to me. It can be tricky for sure. It can be complicated as well, and there may be limitations. But in principle, there's nothing that prevents us from saying that if we know f, we can construct B sub f. Because we really can imagine this just being as a classical computation, and because f itself is just a classical Boolean function, right? Okay. Now, for our current description, imagine f as a Boolean function, but it could be something more general as well that maps n bits to m bits or higher dimensional bits as well. But for our current purpose, it suffices, and as is the case in classical computer science as well, where we're usually interested in this f as being belonging to the class of Boolean functions, which is this object over here, right? You're mapping an n-length binary input to a single bit, right? Now, using these B sub f, there's a nice trick that's quite prevalent in many quantum algorithms that we'll review called phase kickback. The idea being that we are able to take the value of f that we just computed and stored in this auxiliary memory and take this value of f that we're interested in computing and then measuring as well, and actually store it in the phase of the state rather than in the actual state description. What does that mean? Let's work through. So imagine now that these A and B, rather than just being classical labels, are arbitrary quantum states. More precisely, this B now for our computation I fixed to be the minus state. Let's work through it and we'll see. So once we fix B to be the minus state, then I'm applying this protocol. The B sub f is being applied to this input, which expanded out means this. Let's work it out. What would this computation look like? By linearity, you can just pull in the B sub f and write this out as 1 over square root 2. And then what? B sub f directly gets applied to A, 0, minus B sub f getting applied to A, 1. And now our previous classical description of B sub f works, where you can just say, all right, what was the effect. The effect was computing f and storing it in the auxiliary memory. So this would then become 1 over square root 2. Shout out. What should I write? So f hasn't been fixed yet, right? So we'll just take a is the input on which we're computing f. So this would simplify to a tensor 0, which was the initial value of b in this case, but paritied with f of a, right? And the same idea will happen on the other side as well of the superposition. You've got minus a 1 parity f of a. You can think of it as the NOT gate as well. In this case, we are just kind of saying in general, you've got this as the logic gate for parity or exclusive OR, if that's more familiar, right? Okay. And so now what we'll do is just rewrite exactly this expansion by noting the structure of this expansion. If f of a is 0, then note the expansion on the auxiliary qubit is of the form 0 minus 1, right? Whereas if f of a equals 1, then the expansion of the auxiliary qubit is 1 minus 0, which can be nicely stated as just minus 1 to the f of a times 0 minus 1, right? So note that even though in the classical kind of description, we are saying that f of a is being stored in the encoding of the auxiliary memory, auxiliary state, but via this trick, we have been able to move this information f of a into the phase in front of the state rather than the actual state encoding itself, right? So this then means that this expansion over here can be rewritten as, right? So in general, b sub f applied to a minus will give us minus 1 to the f of a minus. So the state description kind of remains the same, but we get this phase shift in front. Kind of clumsy, especially how are you replace the 0 and 1 by 0. So this can really be obtained just by doing a C0, right? So recall the description of C0, if you go back, is also of this form, right? So you're essentially taking the value and parroting into this auxiliary memory. And once you have, if you can perform this, then getting this is essentially something logically equivalent. We haven't really done anything new. We've just rewritten the same state in a slightly different way. Over here, all that we've done is noted that, well, if I fix f of a equal to 0, then this part becomes 0 parity 0, which is 0. And this part is 1 parity 0, which is 1. So you get over here 0 minus 1, if I forget the a. And similarly, in the second case, if f of a equals 1, then this becomes 0 parity 1, which is 1. And this becomes 1 parity 1, which is 0. And so we get 1 minus 0 over here. All right. Why would this be interesting? Well, from what we've been kind of initially saying, when we looked at the teleportation result, when we looked at this nice circuit evaluation that we did in our third session, where we noted that even we were given a description of a 3-qubit circuit, and we asked, well, would the value of the first qubit measured ever be 1? The way we made it work out was by noting a nice amplitude interference pattern happen by choosing the right initial quantum states for the second and the third qubit. So the whole name of the game over here is to be able to perform interference via a manipulation of the amplitudes. And so it's good over here that we are able to store f then in the amplitude, because now we get an ability to now perform a computation and think about it as playing around with the amplitudes of the quantum state that we have, conditioned on whatever is the function f that we applied. So here's a small toy example that we'll build upon. So this kind of model in classical computer science and also in quantum is called kind of an oracle model, where for the moment you imagine I'm not interested in how b sub f was built. Imagine someone just hands you over b sub f, and I'm now interested in performing a certain required computation given that b sub f given to me. And I'm figuring out my kind of key resource that I'll be asking about is how many times do I need to apply the oracle b sub f? Well, if a is in superposition, that's fine. Just like we did the computation over here, you can expand out a and the computation will still work out. In fact, that's exactly what we'll do and is one of the benefits of a quantum algorithm. So towards that end, let's imagine this simple task using a quantum oracle model. So you've got an oracle b sub f that will be given. We are promised that the f that is being encoded is an f over just 2 classical bits. So there's a Boolean function being encoded by the f over 2 classical bits. And in fact, rather than considering all possible f, I've been promised that the f being encoded by the oracle I've been given is from one of these 4 functions. And you can imagine, see these as just a standard kind of basis Boolean function, right? So you f00 just map 00 to 1, 01 will map 01 to 1, and so on. So you have been given this task in which you will be given a b sub f, which encodes one of these 4 functions. And the required task that you need to perform is to figure out which one of these 4 functions f is actually being encoded by the oracle that you've been given, right? So you've just been given the oracle as a black box. You can kind of feed it these 3 quantum states as input over here, and out will come the 3 states that B sub F, based on kind of the structure that we identified over here, is guaranteed to perform. The issue is that based on what comes out and what other computation that I do, I want to be able to figure out which F is being encoded by the oracle that I've been given. Now, obviously, one standard thing to do, even classically, would be to say, hey, all right, let's just query or ask the result for all the 4 inputs. So give it input 0, 0, 0, 1, 1, 0, 1, 1. So that requires us to compute or use this oracle B sub F 4 times, once for each possible input. Can we do better? Classically, no. Classically, if you want a 0 error algorithm, given that the Fs are being picked from these 4 choices, in the general scenario, you do need to query all 4 possibilities in order to guarantee which F you end. Well, you could do 3 queries instead of 4, but just so 2 to the n minus 1. In this case, 4 minus 1. Quantum mechanically, we'll see whether or not there is an improvement. And as already kind of mentioned, what if A was in an amplitude, or A was in superposition? This is our A, right? The first 2 qubits. This is our auxiliary additional qubit. One of the standard name of the games in any quantum algorithm will be to take our input and apply Hadamard on them to get a quantum state that is in uniform superposition of every possibility of length n bit strings. That's going to be a standard technique that's going to be applied in nearly every quantum algorithm. Reduce the inputs might not always be possible, right? So for example, in this case, for some other choices of F, there might be a situation where it's say, hey, there's a function F being picked from K possibilities, such that the function F has this property, that it's only dependent on, let's say, I of the J possible inputs, n possible inputs. So there you could reduce the inputs, but in this kind of current construction, you really have to query it kind of exhaustively, right? The kind of quantum algorithm that we'll have in mind is this. Note that this part over here is essentially just preparing stuff for phase kickback. Apply Hadamard to 1 gives us the minus state. So the auxiliary qubit is in the minus state. Hadamard tensor Hadamard will, as we'll review in detail tomorrow as well, will give us something in uniform superposition. In this case, it will mean I'll get the state 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 over here. And then this is being fed into B sub F. And what will come out is an interesting possibility that we'll kind of review. But let's do the computation first, right? So I'll leave it as an exercise for you to do the computation. That 0, 0, when undergoing Hadamard tensor Hadamard, gives us the state. In fact, you might have already done that in Qiskit. And this is our auxiliary qubit. Well, now we need to apply B sub F. Recall our description of B sub F can be written in this way. So B sub F, when it takes as input this thing, gives as output this. There's kind of this phase in the front, right? So if I take this and give this state as input over here, what would B sub F psi 1 look like? Well, just take each of the individual 4 possibilities in this tensor product and go through them one by one, right? So you'll have half, 0, 0, 0, 0 as input. So you'll have the phase minus 1 to the F of 0, 0 with the ket 0, 0, right? And you can now repeat this description for all of the 4 cases, right? So on and so forth. Yeah, you've got the right idea here. So we've got this state. You can imagine that it would look like this for each of the 4 choices of F, right? So if F was 0, 0, F 0, 0, then this one gives you a minus 1 sign over here, everywhere else you remain plus, and so on and so forth. So those become the 4 possibilities of what will be the state that you will get over here time step t sub 2, condition on whether F00 was there being encoded by B sub F, or F01 or 10 or 11. Now, what do you note about these 4 states? That's exactly what we're trying to get towards, right? So we noted that the phase kickback process allows us to write down the state in this form. The sign has now come up. The value of F is essentially stored in the amplitude in front of the state. And that allows us to make a couple of observations here. We'll do this in much more detail tomorrow when we see Grover's algorithm, but as a precursor to that, what can we conclude based on this? So there's this question mark over here. You may not even want to, you may not even need to perform any other unitary evolution over here and just imagine that, hey, I can actually obtain the answer right away at time step t sub 2. Any comments, observations? These 4 states are undistinguishable. Is that correct? Or indistinguishable? Wouldn't desire to Teleportation says that it is right. So I was just repeating what Bahal said, but yeah, so the idea is, are they indistinguishable or not? And so a quick verification, because we're nearly out of time, And there are multiple ways you can think of it, but if you want to do kind of a brute force computation, imagine you just apply Hadamard over here again on both these two qubits. So essentially make them go through the Hadamard operation and see what comes out at the end in all of the 4 cases. It's a nice observation you should make, that if I finish off this protocol by applying Hadamard and a Hadamard again, and then performing a measurement on both these bits, what do I get as my measurement result? And what's an interesting observation you can make about the measurement results? And then compare it to what we said about the classical situation. And what you will get at the end is something of the form that this is a quantum algorithm that allows you to distinguish between these 4 Fs with a single query, i.e. with a single call to B sub F, whereas the classical variant required you to really query it for all possible input cases. And so here's a simple example of a computational problem where we see an advantage using a quantum algorithm compared to a classical algorithm. But really, it's a very small kind of made-up example, but it introduced this phase kick. So we get a little bit of practice of using the phase kickback trick that we'll see again multiple times. And so what we'll do tomorrow then is to use this formulation of the oracle and this formulation of Boolean functions to solve an actual interesting problem for an arbitrary input size, right? So this was just a made up example with just length 2 inputs, but tomorrow then we work out the details of Grover's algorithm, which solves asymptotically faster, quadratically faster, the problem of unstructured searching, right? But our general idea in terms of how we set up the problem over there is very similar to how we set up the problem over here as well, in the sense that there's a Boolean function encoded by an oracle, and using that oracle, we build an algorithm that solves the problem that we're interested in. This itself is not the example of the square root of an algorithm, but it's a rather small toy example that introduces us to the phase kickback trick that is used to play around with the amplitude signs, right? But we'll see how this builds up to Grove's algorithm. Different applications of mapping an oracle. So we won't have occasion too much to talk about unpacking the oracle and talking about, well, what to do. In general, even within classical computer science, that's not really the purpose of this application. The purpose really is you imagine that the oracle is just given to you as a black box, and the field itself is kind of known as query complexity. And you're interested, query being every time you use an oracle, that's a query. And then query complexity becomes the number of times you need to query the oracle in order to solve the computational task that you're interested in. But for sure, for actual physical implementation, for playing around, let's say for Grover's algorithm, you do need to know how to implement the circuits, but we won't have occasion to talk about that tomorrow. Right? And with that, I'll end for today, and I'll answer a question on Discord if there remain. Thank you very much, Mahlu. That's all for today.
Thank you, Jibran. It is becoming more fascinating day by day. So a brief recap of today. We started with neutral atom quantum computing by Atom Computing and Women in Quantum. There will be no quiz about this part. There were many more questions on the Discord. It is really great how many questions you ask. We sent them to Kristen and we already have answers. So please keep an eye on the Discord. We have answers to several more questions. And then we had Jibran, the 4th session of QBronze, Entanglement and Basics of Quantum Protocols. For this part, there will be a quiz on Canvas about exactly this topic and some Jupyter notebooks to practice. Tomorrow, we have a very exciting session coming up. Let me try to click. Here we go. We will have first Elina Potanina from Blueforce about cryogenic measurement systems, how to get to and measure at 10 millikelvin temperature, almost absolute zero or even lower. And after this presentation, we will learn how this is used to have an environment for superconducting quantum computers, presented by Daniela Bogorin, IBM. How to get to almost absolute zero, and then how to use it for superconducting quantum computers. This will be very exciting. We have some questions from you already from Friday's lecture that we sent to Daniela Bogorin, and she will answer them. Please use Discord to ask questions to these people already, and we will ask them to include it in their lectures. Then further this week, you will finish QBronze, and this will be important to participate in the career fair on August 1st. We have many of the companies that you just saw or will see, Blueforce, Atom Computing, others, come on August 1st, and you can interact with them. And for that, it will be a prerequisite that you finish QBronze by July 25th. So stay tuned with Jibran and finish the quizzes with at least 50% per quiz and 70% in total. And then you can join the career fair. Further this week, a virtual lab tour at MIT on Wednesday will be very exciting. And on Friday, you will learn more about quantum teleportation with a talk about the quantum internet. Pranay Narang from Aliro Quantum. And then on Saturday, a career panel where you can ask questions to experts. Looking forward to that. Please keep asking questions on Discord also for upcoming lectures. And if you are interested in video editing to help us to make nice videos of the lectures fast, please send an email to quantum@womanium.org and we will have you in the team to accelerate our video editing so everyone can enjoy the videos as soon as possible. Thank you very much. Have a nice afternoon, evening, night, and see you all tomorrow.